All regular M&Ms bags have exactly 55 M&Ms. They don't really, but we are assuming that they do for this problem. The M&Ms company tells you that they make 23% of their M&Ms the color blue. That's an important point. If you were to buy 1,000 bags of M&Ms, and if you calculated the proportion of blue ones in each bag, and if you then plotted those proportions on a dot plot, and now we got to answer some of these questions. What symbol will you use for the proportion of blue M&Ms made by the M&Ms company? Well, all the M&Ms made by the M&Ms company, that's a population, so I'm going to use the symbol pi, because that is our symbol for a population proportion. What symbol will you use for the proportion of blue M&Ms in each bag? So I was looking at a bag of M&Ms, and this is a bit of a tip-off for what's coming, because we know that it's going to be a statistic, and we should know that the symbol is p hat. P hat is the proportion for a sample, because statistics come from samples. Notice it says that the sample is blue M&Ms in each bag. In each bag. Okay, why is that important? You'll see in a minute. Do you expect the proportion of blue M&Ms in each bag to be the same? No, we do not. And why? Because of sampling variability. The magic words, sampling variability. So describe the distribution of your sample proportions. I'm telling you, make a picture, and I'm giving you a big hint, shape, center, and spread. So we know we're going to draw our graph right here. But before we can do that, and this is important, we have to check to make sure that the central limit theorem actually applies. We don't know if it applies or not. So we have to use our check. N times pi has to be greater than or equal to 10, and n times 1 minus pi has to be greater than or equal to 10. So what is my n? And this is where a lot of people messed up. My n is my sample size. I have 1,000 bags. I have 1,000 samples, but each bag has a size of 55 M&Ms. A lot of people made the mistake thinking that the sample size was 1,000. You got to look at the difference between the number of samples and the sample size. Now, our pi is 0.23, and is that greater than or equal to 10? Well, I can do this without my calculator because I know that 50 times 0.2 is 10, and 55 and 0.23 are greater than 50 and 0.2. But just to make sure, I'll go 55 times 0.23, and I find out that that is 12.65, so that is greater than 10. I'm good with that one. But n times 1 minus pi, well, my n is still 55. And just to point something out here, we know that the maximum proportion is 100. And we know that 0.3 is less than half of that. So the other side, 1 minus 0.23, has to be greater than that. So I really only needed to check this one. But let's do it anyways, just to make sure. We don't want to make any mistakes. 1 minus 0.23, so 55 times, parentheses, 1 minus 0.23, never hurts to use the calculator, 42.35, that is also greater than or equal to 10. So I can use the central limit theorem in this problem. And the central limit theorem tells me 3 important things. It tells me the shape, the center, and the spread of my sampling distribution. Now remember, my sampling distribution is I'm going to have 1,000 bags. Each of them have 55 M&Ms. I'm going to find the proportion in each bag of blue M&Ms, and I'm going to put it on a dot plot or into a histogram. And what it's telling me is if I do that, then my distribution is going to be normally shaped, that the center is going to be pi, which in this case is 0.23, because we were given that, and that the standard deviation is equal to pi times 1 minus pi divided by n, and I take the square root of that. So again, if you messed up on your n thinking that it was 1,000 instead of 55, that's kind of messing up the whole problem here. So I'm going to get my calculator, and I'm going to go pi, which is 0.23, times 1 minus 0.23, close my parentheses and hit enter. Now I'm going to divide that by 55, which is my sample size. And then I'm going to take the square root of that. I take the square root by doing by making it the exponent of the answer 0.5. So I'm taking it to the 1/2 power. And I find out my standard deviation is, well, let's call it 0.57. I mean 0.057, 0.057. So here's part of my diagram with my integer z-scores on the top. That is, how many standard deviations from the mean I am. Of course, the mean, the middle, is right there in the middle. I'm 0 standard deviations from the mean up here. That's exactly pi. I'm 1, 2, 3 that way, negative 1, 2, 3 that way. And I need to fill in my numbers using the standard deviation that I just calculated. So this is what my picture looks like. So let's use that picture to answer the next question, which is kind of getting to the heart of the problem. Calculate the probability of getting a bag of M&Ms with 11 or more blue M&Ms. And I'm giving you a big hint. I say start by finding what percent or proportion of your bag that will be. Because my x-axis, actually, if I labeled this properly, and I should have, I should have labeled it like this. As you can see, the x-axis are proportions. They're not number of M&Ms. They're the proportion of blue M&Ms in a small bag of 55. And so the problem is saying, well, what if I have 11 in the bag? Well, 11 doesn't really help me, but what does help me is 11 out of 55. And I find out that that is equal to a proportion of 0.20. So now I can look at my diagram here and say, well, this shouldn't be too hard to figure out. 0.20, well, that's between 1.173 and 0.23. So it's right in here someplace, I think. And I'm going to put my proportion down here on the bottom. And I need to find the area here under this curve to the right of 0.20, greater than 0.20, greater than 11 M&Ms. And to find a percentage or a proportion of area, I know that the tool I'm going to use is normal CDF. That's going to give me the proportion of anything under a normal curve. And to do normal CDF, I need a z-score on the left and a z-score on the right. Well, I can see my z-score on the right because I'm looking for everything greater than 20%. Those z-scores are going to go forever. And since my calculator doesn't have a forever button, I know that I'm going to use the z-score of 99. But I need to find the z-score for the proportion of 0.20. So I'm going to use my z-score formula. Let's use a different color. Z equals x minus x bar over s. Well, I'm looking to find my z. The x that I have, my actual data item, is 0.20, my 11 M&Ms, minus the average of blue ones in a bag, the mean, which is 0.23. And I divide that by my standard deviation, which was 0.057. And I get a z-score of, well, let's do it over here together, 0.2 minus 0.23. And I'm going to divide that by 0.057. And I get a z-score of negative 0.53, let's call it. So I'll put my z-score up here, negative, well, let's make it the right color. make it the red. Oh, no, let's make it purple. We'll make it red. Sorry. Negative 0.53, which makes sense because it's between 0 and negative 1. So now I can do my normal CDF, and my z-score on the left is going to be negative 0.53, and my z-score on the right is going to be positive 99. So I'm going to go second, distribution, normal CDF, negative 0.53, comma, positive 99, close parentheses. And I find out, well, it looks like it's a 70% chance or a 70.2% chance. So I have a 70.2% chance of getting a bag of M&Ms with more than 11 blue. Pretty good. But let's continue. You are enjoying eating your M&M data so much that you decide to move on to the family size bags, which contain 275 M&Ms in each bag, exactly 5 times as large as the regular bags. So calculate the probability that you will have a bag with 55 or more blue M&Ms. That is exactly 5 times the number you had in the other question. So everything is being multiplied by 5. Instead of 11 blue M&Ms, I want to have 55 blue M&Ms, and instead of 55 M&Ms in the bag, I'm going to have 275 M&Ms in the bag. So everything is multiplied by 5. So what is different? Well, can I use the CLT, the Central Limit Theorem? Yes, I can use the CLT, and I don't really even need to recalculate it because my sample size has now increased from 55 to 275, and that right there is the key to this particular part of the problem. Because if you were saying that the sample size was 1,000, which is really the number of samples, we still have the same number of samples, but our sample size is different. It's no longer 1,000. So what that is going to change, it's going to change my standard deviation. So it's going to be it's going to be 0.23 times 1 minus 0.23 divided by the new sample size, which is 275, and taking the square root of that. So for that, I get 0.23 times 1 minus 0.23 divided by 275, and I take the square root of that, and I find out my new standard deviation is equal to 0.025. Now that's as opposed to the old one, which was 0.057. So our diagram is going to really look quite a bit different. It's still going to be normally shaped because the central limit theorem applies. It's going to have the same center because the center is the population mean of 0.23. It's going to look like this, and you can see like negative 3 standard deviations is 0.155, and positive 3 standard deviations is 0.305. And if I compare that to before, well, I went all the way down to 0.057 and all the way up 0.401. So this one is considerably narrower. Now, I still have a proportion that I'm looking for of 20%. I have 55 divided by 275, which is equal to 0.20. And that 0.20 is going to fall really, really pretty close here to -1 standard deviations. So let's kind of extend this a little bit. Here's my 0.20. I need to find the z-score for that, which is going to be different because I'm going to have a different standard deviation. So it's going to be 0.20 minus 0.23 divided by my new standard deviation of 0.025, and I get 0.2 minus 0.23 divided by 0.025. I get negative 1.2. So my z-score is negative 1.2. So I'm actually farther away from the mean than I was before, because my mean is 0.23, and when I narrow the size of my bell curve of my normal model, a line that's staying in one single place, 0.20, is now going to be farther away from the mean than it was before. But since I'm looking for everything greater than 0.20, I actually have a larger area to shade. So my z-score is negative 1.2. So I'm going to go second distribution, normal CDF, negative 1.2, comma, positive 99, because I'm going all the way greater than 0.20. And I find out I have like an 88.5% chance of getting a bag of M&Ms with greater than 55 blue ones, greater than 20%. So I'm going to write this here, 88.5%. Which leads me to the last question, which is a little bit difficult sometimes to write out. But even though the numbers were multiples of 5, what changed was the sample size. So when the sample size gets larger, I have less variability. We've heard that before, larger sample size, less variability. So I'd like to think of it like this. I know that the average number of blue M&Ms proportion is 0.23. And if I had a gazillion M&M sample size, like a humongous vat of M&Ms, I would think that the proportion that are blue would be pretty darn close to 0.23, because the sample size is so much larger, so much closer to the actual population size. Well, if I have a super, super, super large sample size, and I know that I'm going to have probably very, very close to 0.23 blue M&Ms, there's really almost 100% chance that I'm going to have greater than 20% blue M&Ms, because the average is 0.23. So because the sample size is larger, I'm much more likely to get bag of M&Ms with a proportion of blue ones closer to the mean, which means since 0.20 is, a certain distance away from the mean, if I have a larger sample size, I'm likely to get a bag that is closer to the actual population mean of 0.23. So, hope that helps.